Alright, I'm going to be going over floating point binary in this video, and that includes stuff like adding and subtracting floating point binary numbers, and normalization as well. You're going to want to know about how to add and subtract binary numbers, as well as 2's complement. So if you don't know about any of that, you should probably watch my previous video on that, and then come back after you've fully understood all that. So in the previous video, I showed you how to represent the integers in binary, right? And that includes negative as well. Well, floating point binary is just used to represent fractions and decimals. So what they do is they extend the table to include decreasing powers of 2. So we've got 2 to the minus 1, 2 to the minus 2, and so on. So if we want to represent a number like 2.25, then we'd want a 2 and then a 0.25. And then we just fill everything else with 0. And then we got a point there. And so this is what people call fixed point binary, where the decimal point is fixed in place. But what if we wanted to represent a really large number in binary? Well, in base 10, we usually use scientific notation to represent very large numbers, right? We multiply by 10 to the power of something. And that's because in base 10, whenever you multiply by 10, it shifts the decimal point one place to the right. So if we multiply by 10 to the power of 7, that's going to shift the decimal place 7 points to the right. And that's the same for binary, but in binary, we're multiplying by base 2, and then to the power of whatever exponent. And that's what's called floating point binary, where we multiply by an exponent, and that shifts the decimal point, like to whatever place you want. So a floating point binary number might look something like this, where this part is called the mantissa, and this part is called the exponent. It's also important to know that almost all the time, you're going to want to have your decimal point, when you're representing a floating point binary number, between the most and second most significant bit, so in between your first 2 digits. Another thing to note is that your most significant bit actually represents the sign. So if your most significant bit is a 0, that means your number is positive, and if your most significant bit is 1, that means your number is going to be negative. So if we want to convert this floating point binary number into base 10, this is how we do it. We'd first convert our exponent into a number. So in this case, it's going to be 4 plus 1, and that's going to equal 5. And what that means is that we are multiplying our mantissa by 2 to the power of 5. And that has the effect of shifting our point 5 units to the right. If, for example, our exponent was negative 5, then we'd be shifting it, we'd be shifting the point 5 units to the left, because that would mean our number would be getting smaller. In this case, it's positive 5, so if we shift the point 5 units to the right, 1, 2, 3, 4, 5, and then rewrite our binary number, with our decimal point here, and then we just convert this binary number using our table. So this represents 1, this represents 2, 4, and this will represent 0.5 and 0.25. So it's going to be 4 plus 2 plus 0.5 plus 0.25, and that equals 6.75. Here's another example of converting a floating point binary number into denary. So to do this, we first convert the exponent into denary. So this is going to be just 2. And so let's rewrite our mantissa with the point. So because the exponent is 2, that's the same as multiplying by 2 to the power of 2. And that has the effect of shifting our point 2 units to the right. So our point is now going to go here. So our mantissa is going to be 010.01. And then if we write down our values for each digit, this is going to be a 1, this is going to be 2, that's going to be 0.5, and that's going to be 0.25. So we have a 2 and a 0.25, so that's just going to be 2.25. Now, in this example, we need to convert from a denary number to a floating point binary number. This one is slightly different because we have to represent a negative number. So that means that our most significant bit needs to be a 1, right? But first, let's represent this denary number as a decimal. So minus 2 and 5/8 is just going to be minus 2.625. So if we remember how 2's complement works, the most significant bit is going to be a negative number, and then we add on whatever is remaining. So we know it can't be minus 2, because if we're going to add on to minus 2, that's going to be bigger than whatever number we're trying to represent. In this case, minus 2.625. So our most significant bit is actually going to be minus 4. So that's going to be a 1. So now we need to find out what to add to minus 4 so that we can get minus 2.65. So we can't add 2, because then we'd get a number greater than minus 2.65. So the next best thing we can do is add 1. That will give us minus 3. So we need to add on a 1. And then to go from minus 3 to minus 2.65, well, we know if we add 0.5, then our number will be too large. So we need to add on a 0.25. Minus 3 plus 0.25 is going to be minus 2.75. And then we can notice that we can also add on 0.125 to get what we're looking for. So our fixed point binary number is going to look something like this. But they want it in floating point binary number. So we need our point to be between the first and second digit. So over here. And we also need the exponent. So if we're shifting the point 2 units to the left, then to compensate for that, we need to multiply by 2 to the power of 2, right? Because that would shift our point 2 units to the right. So if we have 1.01011, then we need to have an exponent of 2. So they want a 4-bit exponent, so that's just going to be 0010. And so our final answer is just going to be this, but without the decimal point, because we don't represent our answers with the decimal point. Now on to normalizing floating point binary numbers. So a problem that occurs when trying to represent very large numbers is that there's different ways to represent the same number. For example, in base 10, we can represent the same number twice by doing something like this. And what this might look like in binary is something like this, right? So we have a floating point binary number, and if we convert that to a fixed point, and then convert that to denary, we get 24.0. But 24.0 can also be represented with this floating point binary number. And so, well, we fix this problem by just picking one standard. So usually in scientific notation, this is considered the correct one. And when you're normalizing floating point binary numbers, if the number is positive, then the decimal point needs to be before a 0 and after a 1. If the number is negative, then the decimal point needs to be before a 1 and after a 0. So I'm going to go over an example of how to normalize some binary numbers. So if I rewrite this binary number, 00011, 0010, and we have our decimal point between the first 2 bits, then because we know the number is positive, we want to move our point over here. between the 0 and the 1, right? So that's going to be a shift of 2 units to the right. So if we're shifting the point 2 units to the right, to compensate for that, we need to subtract 2 from the exponent. So our normalized result is going to be 0.11, and then they want a 5-bit mantissa, so we just add 2 like useless bits on the end. And then we need to subtract 2 from the exponent. So currently the exponent's already 2, so our exponent is just going to be 0, 0, 0, 0. For this next one, we know that the number is negative, so we need to move this point 2 units to the right, because we want it to be before 1 and after 0. That means that we also have to subtract 2 from our exponent. So our exponent currently is 6, so we need to subtract 2, and that equals 4. So our exponent is going to be 0, 1, 0, 0, and our new mantissa is going to be 1.0000. Now on to adding floating point binary numbers. My method for doing these types of questions are just converting them to fixed point and then performing just your regular binary addition and subtraction methods from there. So if I convert our first number to fixed point, our exponent here is 2, so we need to shift our point 2 units to the right. So it's going to be 0.11. And for our second one, our exponent is 3, so we need to shift this one 3 units to the right. 1, 2, 3, and we get 0.0. We get 0100.0. And now we just add the binary numbers like how we did it with the integer ones. So this is our binary number, but they want it normalized. So to normalize it, we want our point to be between the 0 and 1, right? So we need to move our binary number, or move our point 3 units to the left. 0.111. And remember, they want a 4-bit mantissa, so we disregard the 0 there. And because we moved it 3 units to the left, to compensate for that, we need to multiply by 2 to the power of 3. And that's going to be our exponent, right? So we need to represent this 3 in our exponent. So that's going to be 0011. And that's the answer. Lastly, I'm going to show you how to subtract floating point binary numbers. I'm just going to do the same method and represent them as fixed point, and then subtract from there. So we have 010010, and our exponent is 4. So we need to shift our point 4 units to the right. So it's going to be 0, 1, 0, 2, 3, 4, 0, 1, and then a point. And let's convert our second one. 010010, and our exponent here is 2. So we need to shift our point 2 units to the right. 1, 2, 1, 0, 1, 0, 0, 1, 0. Alright, and then we just put our binary numbers on top of each other and subtract from there. So we can't do 0 minus 1, so we need to carry some digits from previous ones. That's going to be 2 minus 1, which is just 1. 1 minus 0, which is 1. A point there. 0 minus 0 is just 0. And then we need to carry carry more digits. 1. 2 minus 1 is 1. 1 minus 0 is just going to be 1. And there's also another 0 after this one. So this is our result as a fixed point, but we want to represent it as floating point, right? So we want to move this point to, between the 0 and 1. So that means we need to shift it 1, 2, 3 units to the left. So that's going to be 0.11011. And we don't write this 0 because they want it in 6 bits. And it's also not that significant. And because we shifted it 3 units to the left, to compensate for that, we need to multiply by 2 to the power of 3. And our exponent is 3, so we need to represent 3 as our exponent. And that's just going to be 0, 0, 1, 1. And that's the answer.